Please start.
Recording in progress.
Okay, let me start. All right, so yesterday we talked about basics of quantum computation and quantum information theory. And today we're going to actually talk about some quantum algorithms that are useful for simulating physical systems. And I would argue in this first lecture that for solving most of the problems using quantum algorithms, what really matters is what we call as Hamiltonian simulation. What I really mean by that is that I'm given a Hamiltonian H, and I would like to apply this time evolution e to the minus IHT to some arbitrary quantum state on a quantum computer. So here are some motivations. So we all know that interacting quantum many-body systems are difficult to solve unless there is a very special structure underlying the problem. And what we would like to have, but we don't, are something like this. We would like to have an algorithm for preparing the ground state so that you can, for example, measure correlation functions from the ground state wave function, and you'll be able to measure the order parameters to determine what phase you're in, for example. And you would also like to maybe have an algorithm for preparing a thermal state. So you give me any finite temperature and a Hamiltonian, and I would like to prepare a thermal state defined on that temperature. Again, the goal will be to compute correlation functions. And something that is extremely difficult these days is something like dynamics. So if you want to simulate dynamics of a quantum many-body system on a classical computer, this is extremely costly. So much less work is done on the dynamics front compared to the ground state and thermal state, at least for the classical algorithms. But that's mostly because this is difficult. It doesn't mean that this problem is not interesting. So it'll be good to have these list of problems, some general purpose algorithms for these problems. I'd like to point out that for some of these problems, there are good reasons to believe that you shouldn't expect there to be a general purpose, efficient, classical, even quantum algorithm to solve these problems. So here's the basic argument. So this is, so I'll just go through this. So it turns out that there's a mathematical fact so that you can reduce any problem in NP. So problem in NP, an example of that is basically solving the ground state energy problem of a spin glass model. Let's say for simplicity, you assume that the spin glass model is very simple. So the coupling constants are either like +1 or -1, so that you either have a ferromagnetic or anti-ferromagnetic interaction. And what you're asked to do is to determine if the ground state energy is 0 or not. So that's the question. So it turns out that any problem in NP, I won't explain what NP is, but for the purpose of this lecture, you can think of them as a large enough class that includes very difficult problems to solve efficiently. So it turns out that any problem in NP can be reduced to the problem of solving this ground state of the spin glass problem. So if there is an efficient quantum algorithm for preparing like any ground state, so let's say I give you a Hamiltonian and you have a capability to prepare any ground state of that Hamiltonian, then you can compute the energy efficiently by simply measuring the individual terms of the Hamiltonian on the quantum computer. So in particular, you can check if the ground state energy is 0 or not by just simply estimating the ground state energy. Okay, so everything that I said so far can be made to be completely rigorous. And here's the part that is not completely rigorous, but plausible. So it turns out that despite many attempts, there does not seem to be an efficient quantum or classical algorithm that can solve all the problems in NP efficiently. So this is a fact, so we don't know such algorithms. That said, we cannot prove that such an algorithm exists. But the evidence suggests that there probably is no general purpose efficient classical algorithm for solving problems in NP, even if you have a quantum computer. So most likely, There's probably no quantum algorithm that can find the ground state of arbitrary quantum many-body system. Yeah. Question? There
Can
is a
you a
question.
little bit more explain about what is the spin class?
Yeah, so for example, let's say I have a spin 1/2 particles, and the Hamiltonian is, sorry, I don't have much space, but I'll just zoom it up. So let's say Hamiltonian is a sum of, what should I call it? Yeah, I call it as Ji, Si, and this is +1 or -1, and Si is essentially like a product of like the angular momentum in the z direction. Let's say Z1, Z2, Z3, or like Z1, Z2, Z5, Z6, things like that. So any model of this form. So it's a completely classical model. Of course, for general spin class, J doesn't have to be +/-1, but I'm saying that even if you make your problem easier by restricting it to the case where J's are +/-1, this problem is still hard. So the point is, there are good reasons to believe that you cannot have a general purpose algorithm that can solve these problems. And the same can be said about the thermal states as well. So unless if you go to a high enough temperature for which the high temperature expansion works. If you at low temperature, we don't have a general purpose algorithm. And but another side note is that for classical systems, but nevertheless, there is a pretty practical algorithm that works fairly well in most cases, and this is known as the Metropolis algorithm. And generally speaking, there's no like rigorous guarantee on the efficiency. So if you have a model and if you come with some Metropolis algorithm to solve this model, like generally speaking, it's not easy to guarantee that you will converge to the right answer in polynomial time. But it works well in practice. So you might ask, like, if there's like a quantum version of the Metropolis algorithm, and the answer is yes. Again, there's no guarantee on the efficiency, but under some plausible assumptions, like Eigenstate thermalization hypothesis, you can expect this to work efficiently. And in all of these works, so I should say that there are no general purpose efficient algorithms, but there are these algorithms which finds either the ground state or prepares a thermal state under some conditions. And if you look at how these algorithms work, which I won't explain in this lecture, it essentially boils down to using a subroutine called quantum phase estimation. And this is really a key subroutine that is used in many of the quantum algorithms. So I'm going to explain what this is. And once I explain this, it'll become obvious why I am so fixated on simulating the time evolution. Okay, so I'm going to talk about the quantum phase estimation. So a single sentence summary of the quantum phase estimation would be a unitary transformation which achieves the following. So suppose you're given a Hamiltonian, and here I wrote down the eigenvalue decomposition of the Hamiltonian. So here En is the energy of the eigenstate n, and n is just an energy eigenstate. And quantum phase estimation, what it does is the following. So basically, suppose I am given an eigenstate n, and I have another state initialized to some particular state, let's say the 0 state, and then I apply some unitary transformation. And after that unitary transformation, I obtain a new state. So the state of this n remains as is, but the state of the 0 is changed to something else. It gives you essentially the energy up to some proportionality constant. So that's what the quantum phase estimation is trying to achieve. It's some unitary transformation that, given h, somehow reads off the energy corresponding to this energy eigenstate. there's a bit of a practical issue. So what I just said is technically speaking, not exactly correct, because if you have a physical system, then its energy will not be some like round number. It'll be some, in order to specify it exactly, you will need infinite precision. And obviously you cannot do that you cannot write down an infinite precision number on a finite dimensional quantum state. Especially if you only have a finite number of qubits, you cannot hope to write down En very explicitly. So when I wrote this down, what I really mean by that is that I'm essentially trying to find a unitary transformation. There's a question. What is the difference between N and En? So maybe, okay, so good. So N is the, good. So N is the energy eigenstate. So let's say, and En, this is the state that is encoding the value of En. So let me give you an example. Probably that'll be easier to explain. So let's say H is a 2x2 matrix. So it's 0.1, 0, 0, 0. Good. So, okay. So in this case, let's say E1 in terms of, so this would be 0.5 and E2 would be 0.75. So I'm just trying to record this information in finite number of bits. So in the binary representation, this would be 0.1. And in the binary 0.10, just to be concrete. And in the binary representation, this would be 0.11. So I guess in this case, E1, I would record it as 10, and E2 as 11, something like this. Good. All right, so yeah, in practice, so here I chose round numbers so that I can write this down as like 10 and 11. But for example, if I have something like this, E1 and E2, I won't be able to exactly write them down in 2 bits. So it's more like I'll have an approximation of E1 and E2, which I write down as E1 prime and E2 prime. So that's what we have here. But modulo those little subtleties, this is essentially what we're trying to achieve. So I'm going to show you the quantum circuit that realizes this operation in a certain limit. So quantum phase estimation can be implemented using 2 subroutines, which you're probably all very familiar with. One is the time evolution operator. So you give me the Hamiltonian, I can define a time evolution operator for a certain set of values for this time t. And the other thing is the Fourier transform. So the actual name is quantum Fourier transform. And this is just the discretized version of the Fourier transform when you change from the momentum basis to the real basis, for example. And I'm going to be more explicit and actually write down this transformation in the next page. But for now, I'll just, at the high level, explain to you how this procedure looks like. And here's the quantum circuit. So this is, so like last time I said, for individual qubit, I draw a single line, but obviously in this case, the system on which the Hamiltonian axon can have more than 1 qubit. So this is really consists of many qubits. So I know that I'm somewhat being inconsistent with the convention, but think of this as like an n qubit system for some n, okay? And we could put in any quantum state here. but it'll be very convenient to begin with an energy eigenstate. And later I will tell you what happens if we don't have an energy eigenstate here. But in any case, here you start with an energy eigenstate. And then you have another set of qubits, and those qubits are initialized to a particular state called the uniform superposition state. If you look at the expression, you'll see why. It is a superposition state with the equal amplitudes. Here, big N is just some number that we're going to choose later. Okay. So this is our beginning state, and then we're going to apply a particular unitary transformation. So we're going to apply something that looks, something that is very much related to the time evolution, but slightly different. So let me show you this. So I'll first draw the diagram, and then I'm going to explain to you what this means. If it is not clear, please let me know, because this is important. So in circuit diagrams, so here you see I wrote down N, that means the input. So what I'm saying is that if the input is K, then I'm applying e to the minus IHK to N. More explicitly, suppose, let's call this entire unitary as U1. What I'm essentially saying is that if I apply this unitary U1 to a state of the form K tensor N, it acts as K tensor e to the minus IH K applied to N. Okay, so that's what this unitary is doing. So what you can think of K as an integer. It tells you like how many times you're going to apply this e to the minus IH times 1. So you're starting with this uniform superposition state on which defines the number of invocations of e to the minus IH times 1. And this is the unitary that you have. So any questions so far about the definition of this unitary? Okay, if not, I'll move on to the next part. Then what you do is that you apply a quantum Fourier transform, which I'm going to show you. I'll write down an explicit equation in the next page. And then what you do is that you measure. This looks like a beater. This means that you're measuring all these qubits. So let me, before I move on, actually, let me make a brief comment. So, so suppose I know how e to the minus e to the minus IH looks like. So that is to say, suppose I know how to decompose this unitary into a sequence of 1 and 2 qubit gates. Then from that knowledge, how would I actually construct this thing? Yeah. Well, it's very simple. So what you would do is that you think of K as a binary representation. So think of this as let's say I have like a 3-bit number. What I would do is something like this. So this top thing will basically represent the lowest significant digit of the number K, and then the second thing will represent the second significant lowest significant digit of the number, and the third one will be the next digit. So you can see that in this first part, you're applying it once, you're applying the control unitary once. In the second part, you're applying the control unitary twice. And the last part, you're applying the control unitary 4 times. And you can convince yourself that this actually realizes this unitary U1. So if you know how to decompose, if you can decompose e to the minus IH into 1 and 2 cubic gates, you can decompose this unitary U1 into these individual control unitary. And in the last lecture, we've learned that these control unitaries can be constructed out of construction of e to the minus IH. So all of this can be done in a very straightforward way. Good. So having established that we can actually construct a circuit, except for quantum Fourier transform, which I haven't explained to you. Now, let me define what quantum Fourier transform is and analyze how this circuit behaves, what this circuit actually achieves. So here's the circuit that I drew from the previous slide. And the quantum Fourier transform is defined in the following way. So without loss of generality, let's say I have an integer x. Then under quantum Fourier transform, quantum Fourier transform is a unitary transformation which acts on every basis set in the following way. Okay, so you can see some similarities with this and the continuous version of the Fourier transform. And so let's just go through this circuit and see what happens. So in the beginning, you begin with the following state. And let me remind you that N was the energy eigenstate. And the next step is that we apply this unitary U1. Okay, so what does that do? Well, what it does is that if this first ket is K, then it applies the unitary transformation, which is e to the minus IHK applied to N. But remember that N is the energy eigenstate, and therefore applying this thing to N gives you a scalar. And of course, once you get a scalar, you can move that thing around. So I'm going to get that thing over here. So e to the minus I E N K is a scalar. You can think of it this way. Yeah. So next step is that we apply the quantum Fourier transform. And then what we're going to get is that we're going to get a double sum I literally just plug in the expression. And then what we do is that we exchange this sum, which is totally possible because both the sums are both finite. Okay, so I'm going to move this N over here. So this thing in the middle, let me emphasize this part. So this thing in the middle, that's a function of y, yeah. And you can sort of, like if you're a physicist, you can sort of guess what this thing is. So in the n goes to infinity limit, you have like, if like what's over here is 0, then you're not oscillating. But like, okay, so you're basically summing over like these different phases. And we know that if this thing is like not 0, then like these things will oscillate. When you average them out, they will become very small. But if this thing is 0, all the phases will be aligned. So you're going to basically get a sum of exponential of 2 pi I k times 0, sums from 0 to n minus 1. So in that case, you're going to get like a 1. But otherwise, you're going to get something that is extremely small. So essentially, you can think of this as like some sort of delta function, like not the direct delta function, but a function that becomes 1 when this thing is 0 and 0 otherwise. Okay. So at the end of the day, what you're going to get is, roughly speaking, so that means that y over n should be equal to 2 pi divided, en divided by 2 pi. So essentially what you're going to get is n divided by 2 pi times n tensor n. Okay? And 2 pi is just some numerical constant, and n is a number that you can just choose. So if you want the better precision, you just choose n to be a larger number. So what we saw is that by running through this circuit, which be somehow some of these gates were removed. So in any case, coming back to where we were, by running through this circuit, we realized that if we perform this measurement, what we're going to measure with high probability will be some constant times the energy the eigenenergy of this state n. Okay? So that's one of the things that the quantum phase estimation is very good at. It's a process to read off the eigenenergy if your input is the eigenstate. Any questions so far?
I have one quick question. So when you apply the QFT block, in the diagram, the QFT block applies in the line in the top, but it doesn't apply.
Yeah, only on the top, yes.
Right, but if you look at the state in your analysis equations in the bottom of the screen, aren't you including both the top and the bottom?
Yeah, so this QFT, it only acts on this first ket, so it's an operator that acts on this Hilbert space spanned by these k's. So I am still keeping track of this n,
okay.
but like it's that is not really doing anything at this point.
It's not doing anything. You're right. Okay, thank you.
Yeah. Any other questions? If not, I will move on to the another aspect of quantum phase estimation. So what is the main lesson so far? We had a simple circuit and called quantum phase estimation, and that circuit allowed us to estimate the eigenenergy if we are given an energy eigenstate. But there's another way to view the quantum phase estimation, and we can view it as a eigenstate filter. So what do I mean by that? So in the previous setup, we assumed that we began with the energy eigenstate n. So this was the energy eigenstate. And after you run the QP, you got, so there was some numerical constants, but let me just ignore them. Up to some numerical constants, maybe I'll call them as En prime. We obtained this new state, right? And it's interesting to ask what happens if we started with some general quantum state, which is a superposition of different energy eigenstates. So let's say I begin with this very general form of states, and then I apply QPE. Remember, the quantum phase estimation is a unitary process. I mean, like there is a measurement part here, but like up to this point, up to QFT part, everything was unitary. So using the linearity of quantum mechanics, we can see that this will become and oh, sorry, I think I flipped the order. Okay. All right, better. So by linearity, this is what we're gonna get, yeah. So in the next step, in the final step, like here, we performed a measurement, right? So when we do that, so we're performing a measurement. So depending on your measurement outcome, with probability of alpha and absolute value squared, the post-measurement state will be the energy eigenstate, yeah? So this is very interesting because this is one possible applications of quantum phase estimation. So suppose, for example, let's say you have some many-body quantum state, which is not exactly the ground state of the system that you want to, that you care about. Let's say you have, like, let's say some quantum state psi, which has, let's say, like an overlap of like 1 over square root of 2 with the ground state, and 1 over square root of 2 with some excited state that we don't care about, that we do not care about. So from a perspective of energy, like this excited state can have a very high energy. So in some sense, this state psi can have a very high energy compared to the ground state. But as long as you can ensure that you have a high enough overlap with the ground state, you can prepare the ground state by preparing this state psi and running the quantum phase estimation. And with probability of 50%, you will be able to prepare the ground, like the true ground state. So this is one thing that quantum computer is very good at. It's very good at like selecting out an energy eigenstate. So these two things are the primary applications of the quantum phase estimation. So to summarize, this quantum phase estimation, for this part, you're going to have to just take my word for it. But these are really the key subroutines in many, many quantum algorithms, such as ground state preparation and thermal state preparation. And when it comes down to the implementation, they can be decomposed into controlled time evolutions and quantum Fourier transform. And oftentimes, again, you're going to have to just believe me for this, but almost always the complexity of the time evolution completely dominates that of the quantum Fourier transform. So quantum Fourier transform has a very, very negligible cost. So the key point is that for many useful quantum algorithms, they reduce essentially down to the application of quantum phase estimation. And quantum phase estimation essentially boils down to time evolution. So that's why people often care a lot about optimizing time evolution. Yeah, there was a question.
Okay, so I have a question. So can you go back to the previous slide that you have the unitary operators? Okay, here that, for example, for the given Hamiltonian, I need to write down this unitary, I need to realize this unitary operator in the quantum gate.
Mm-hmm.
So can you give some kind of concrete example for some
Yeah.
simple like a harmonic oscillator? How can I realize them as a
Oh,
quantum gate?
so harmonic oscillator is kind of more difficult because it's infinite dimensional, but I can. So you're asking about this part, right? Like, can you see my red dot?
Yes, yes.
Yeah, okay. So there are really two parts to this. So let me first copy this. So this can be essentially broken down into this controlled time evolution. And if the Hamiltonian is, so if you know how to break down e to the minus ih into like 1 and 2 cubic gates, this becomes very easy. And I guess I'm going to show you one example later, but like one very trivial example would be again some like Icing model. Let's say like a 1D Icing model, then e to the minus iht will be so these little blocks are individual gates, and this is basically e to the minus I c1 c2 t, and this would be e to the minus I c2 cc c3t. So this would be a fixed time evolution, and you're just going to have to make a controlled version out of this. So how do you do that? Well, let me make a new page actually. So let me copy this entire thing. So let's say I want to make a control version of this. Then what I would do is so the gate over here is changed into a controlled 2 cubic gate. And the gate over here is again changed into another controlled 2 cubic gate. Another one here, and another one here, another one here. So I guess like for this example, this okay, these like individual blue boxes, they can be decomposed into this way. So you just stack all those boxes together. But the difficulty with the harmonic oscillator is that I will first need to convert the basis for the harmonic oscillator into a qubit basis. So I'm going to have to first truncate to some like finite energy or like finite n, right? Let's say from n from like 0 to some number. And then I guess I'm going to have to somehow re-express the creation and annihilation operator in terms of gates. I'm sure it can be done, but I can't think of it. I can think of a way to do that right now.
Sure. Yes. So here, for example, e to the I minus I g1 g2. Then in this unitary, I need to explain this matrices in terms of these bases. Then I can use some like two cubic gate to approximate this, right?
Mm-hmm. Yeah, yeah. I mean, I can. Yeah, for this one, I can even tell you how. So, like, yeah, you're right. So you should map it into this one. C1, C2, T. So, and in this case, what I would do is something like this. So it turns out that Z1, Z2 is actually equal to Cx, X, Z2. What I mean by that is Z1, Z2 is actually equal to I guess I didn't need to write down 1 and 2, but this is a fact. It's something that you can verify. So this will be essentially okay, got it. So this thing over here will be e to the minus I z to t. So you basically have a 2-qubit gate, which is a C0 gate here and here. And this thing in the middle, this is a 2-qubit gate controlled on here. So it's a controlled e to the minus I z t gate. So in this case, you would be able to break it down into 2-qubit gates like this. Okay. There are no other questions. I think I'm going to move on to the time evolution. So I'm going to give you like the simplest possible. Actually, so I should note that in the example that I gave you, like this one was kind of trivial because all the terms here, they commute with each other. But in quantum mechanics, we know that operators do not necessarily commute with each other. And when you write down a Hamiltonian, indeed, some of the terms will not commute with each other. And it's not obvious how you can deal with them. So to actually simulate time evolution for interesting Hamiltonians, we need to have a way to deal with these operators that do not commute with each other. So this time evolution, I hope I was able to convince you that there's a lot of like application motivation for thinking about this. There has been a lot of very fruitful development over the past 20 years. So the oldest of those, which I'm going to talk about in this lecture, is the Trotter Suzuki decomposition. Once you see the formula, you'll just see immediately what this is. And then starting around like 2000s, like people started developing new techniques called as linear combination of unitaries and quantum signal processing. In the next lecture, I'm going to very briefly going to tell you about the idea behind this, but they have their own pros and cons. And what I want to do today is to explain to you how Trotter Suzuki works. But before I do that, I think it's important to understand, like, when people write these papers, it's important to understand like what they're really trying to do and what their objective is. So let me first begin with that part. So in an ideal world, what you would like to do is you'd like to implement e to the minus IHT perfectly with no error. But this would be a hopeless task. Like there will always be some approximation error. So what you should really aim to do is to implement some unitary U such that U applied to any state is very close to e to the minus IHT applied to the same state. And we can formalize this by saying that the distance, some sort of distance between the two as a state vector is upper bounded by some error, let's say epsilon. So this epsilon is some number that you can later determine, like 10 to minus 3 or 10 to minus 10, like whatever you want. So that's the goal. And this means, well, like to be a little bit more conservative, what we really want is that we want to say that no matter what the input state is, no matter what the psi is, we want the action of U and the action of the actual time evolution, e to minus IHT, to be very close to each other. no matter what psi is. And this is what's known as the operator norm. And the reason why I'm telling you about this is because when it comes down to approximating the time evolution unitary, what people are really trying to do is to construct U such that U minus e to the minus ist in operator norm is small. This is the problem, this is the technical problem that people are trying to solve. And the motivation behind that is given from this analysis. And this is a bit pedantic, but I think it's elementary and easy enough to explain that I think it's good to just tell it to you. Operator norm is a norm, so it satisfies the triangle inequality. So if I have two operators, then they're just upper bounded by the norm, the sum of their respective norms. And if you have two operators multiplied together, they are upper bounded by the operator norm of those individual operators. And another simple thing that you can check is that if you have a unitary, it has an operator norm of 1. This is easy to see because that was the definition, but that's just simply this, but U dagger U is identity, so that's just 1, no matter what psi is. So these are the basic properties of the operator norm. So let me give you some exercise, which is, so let's try to work this out together. So here's a problem. So suppose I constructed a unitary which approximates the true unitary evolution with some error epsilon. Suppose I apply this unitary like n times, then what would be the error that is incurred? So this is like a routine thing that people would ask, like when you study these algorithms. And the technical problem would be this one, like how would this depend on n and epsilon? And it goes as follows. So for a simple case, let's consider the n equals 2 case. In that case, what I'm going to compare is that I'm going to compare u squared to the e to the minus 2i. So how would you actually found this? Well, I'm going to show you the following decomposition. Hope that was okay for everyone. And then we can use the triangle inequality. And then what do we notice? We notice that unitary u, well, then we can use the fact that this is the operator norm is sub-multiplicative. Fancy way of saying this inequality. So then what do we see? We see that both unitary u and e to the minus ist are unitary operators. So this is 1, and that's also 1. Therefore, this is that's equal to this thing, which is upper bounded by 2 epsilon. Okay, so where did it? So what did we use? So let's say from here to here, we used triangle inequality. And then we use the sub-multiplicativity. And then from here to here, we use the fact that unitary has an operator minimum 1. These are like the standard ways in which people prove things. And I suggest to you as an exercise to prove that this is upper bounded by n epsilon. This is intuitive because small error in the worst case can at most scale linearly in the number of time steps that you apply this unitary. Good. And another exercise that I can suggest to you is the following. So again, starting from the assumption that unitary, this u and e to minus IHT are close to each other in epsilon, you can show that these two expectation values are close to each other. This is another exercise which would follow pretty straightforwardly from the tools that I've shown you in the previous slide. But now let's move on to the actual technique for the Hamiltonian simulation, which is the Trotter-Suzuki decomposition. So here's a single formula that explains the Trotter-Suzuki decomposition. The thing that we want to actually do is that we want to apply e to the minus IHT, and we can do this by basically taking the n goes to infinity limit of this formula. And the reason why this works is because at least when the n goes to infinity limit, this becomes identity minus IATN, identity minus IPN, plus some subleading terms in 1 over n. And this is I minus I, A plus B, n over T, plus some terms, subleading terms, which is roughly equal to e to the minus I, A plus B, T divided by n. So you then take exponentiate with n, then you get the left-hand side. So that's the basic idea behind the Trotter-Suzuki decomposition. And really the game here is try to find a decomposition which converges to the left-hand side in a better and better way. And as you could imagine, the simplest of such things would be simply approximating this e to the minus IHT by this thing for a sufficiently small t. And it is not too difficult to convince yourself that at least as t goes to a very small number, the left-hand side and the right-hand side will be very close to each other. And the basic reason is that we can just simply Taylor expand both sides and compare them order by order. And as I've shown in the previous slide, on the left-hand side, what we're going to get is I minus IHT minus IHT squared plus da da da. And on the right-hand side, we have plus da da da. And as we've seen, the leading order is the same. The next leading order, minus IHT and minus IAT minus IBT, they match. If you check the next order, you'll see that they actually do not match. So the error between the difference on the left-hand side and the right-hand side is order t squared. Okay. So that's so with this, you can plausibly believe that the total error would be roughly like a big O, roughly like a t squared. And let's see. So if you want to evolve for a time of t, then you choose t equals to be large t divided by n, and there will be a total of n steps. So the total error will be roughly big O of t divided by n squared times n, which is big O of t squared divided by n. So as you make the n get larger and larger, you can make the total error like a smaller and smaller in a very systematic way. So, but the issue, so that's the old Trotter Suzuki decomposition bound. But the issue with the previous approach is that the bound becomes very lousy when A and B commute, right? Because when A and B commute, we know that e to the minus IHT is exactly equal to e to the minus IAT times e to the minus IBT. So this is just exactly correct. So somehow the bound that we have here does not seem to take into account the fact that when A and B commute with each other, you can do much better. And what people have been working on lately is what people call as the commutator-based bound. And these are the bounds which actually takes care of this subtleties in a nice way. And although the higher order versions of these things are like fairly complicated, the lowest order version is actually pretty intuitive and interesting. So let me show you, let me give you a flavor of how these things work. So the idea is that you try to construct a unitary, which when t goes to 0, becomes an identity. So here's a candidate for that. And indeed, when t goes to 0, you get something, well, you get an identity. And moreover, you can sort of guess that the 0th order and the 1st order terms will all cancel out each other. So if you take the derivative, what happens is the following. So we take the derivative. First, you have e to the I t. So I'm going to pull out the I to the front, and I have a. So I just took the derivative of the first term, and then I have e to the I t. So t b e to minus I t minus e to the I t e to the I b t a plus p e to the minus IHT. You can see that this b and that b cancels out each other. So you're left with this term, which is e to the IAT a IBT minus IBT a to minus IHT. And here's the thing. So we can simply rewrite this as identity plus the following expression. And we can subtract identity from both sides, and we get this. And the thing is, let's say I want to estimate the operator norm. I'm going to get that, but then we can use the triangle inequality. And that triangle inequality simply is this expression. So I stare at this expression, and what I see is that in the front, I have e to the IAT, which is the unitary, which is a unitary, and I have e to the minus IHT at the back, which is another unitary. So we can just kill those things in the operator norm. And then what we're left with is something that is really nice. And here you can really see that you can sort of guess that this expression is actually upper bounded by the commutator of A and B. The reason is I can take the derivative of this guy again, and that's simply b e to the minus I b t double prime e to the I b t double prime d t prime d t prime, which ends up being, after removing both these unitaries, it becomes 1/2 t squared commutator of A and B. So this is a flavor of how people prove the so-called like commutator bound. So you somehow like concoct a unitary so that the only thing that you're left with is a commutator between these like potentially non-commuting terms of the Hamiltonian. So therefore, we have concluded that the Trotter-Suzuki decomposition yields an error, which is on the order of the commutator between A and B times t squared. So for approximating this unitary, which is e to the minus IHT, the error then becomes this commutator of A comma B, t squared divided by n. So yeah, so let's finish this lecture by completing some like a complete case study. Okay, so I'm going to give you an example model. So this is known as the transverse field Icing model in one dimension. So we could solve this model completely, but this is just a model to like explain like how would you actually estimate the cost of performing a Hamiltonian simulation of this model. So in this case, I would simply write down A as the first term and the B as the second term. Okay. And we have seen in the previous slide that the total error would be upper bounded by t squared commutator of A and B divided by n, where n is the number of time steps I'm going to choose. So, okay, so what does that mean? That means that we are approximating e to the minus IHT into e to the minus A divided by t divided by n, e to the minus I b t divided by n, repeated n times. So a natural question is like, how many gates do we need to actually implement this first part? And how many gates do we need to actually implement this second part? Yeah. Well, A is simply a sum of commuting terms. So A can be decomposed very straightforwardly. So e to the minus IA and t would look like this. So these blue things are the gates that are used in implementing e to the minus INT. So I guess if we were to be super more specific, this would be e to the minus I lambda C1, C2 times t divided by n. It's summed 2-qubit gate. What about e to minus IB divided by t divided by n? In that case, we're going to have these single qubit gates, right? Because if you look at B, this is a sum of xi. So if you exponentiate them, all of them commute with each other. and every single one of them will be just single qubit gates. So if you have like n qubits, then the total cost will be O of n, 2 qubit gates, and O of n, 1 qubit gates. And therefore, the single step, this is what people call it as a single Trotter step. So a single Trotter step will cost On gates. By gates, I mean like 1 or 2 qubit gates. And how many Trotter steps are we applying in total? This is the total number Trotter steps. So the gate complexity would be big O of n times n. So the only question at this point is if we want to have an error of epsilon, like what's the n that we should choose? And that's of course very simple. It's simply, well, we have this formula. So from this we can determine what n should be. And the only thing that is not completely clear is what this commutator is. Well, that is simply so I can get a much better bound, but I'm going to be a bit lousy to make the analysis slightly simpler. So this is just a commutator. So then we have, then what do we have? We have a triangle inequality, and therefore this is AB plus BA, and that's upper bounded by 2A. But the thing is, A and B, assuming that lambda is over 1, so like order 1 constant, A and B both consist of at most like n terms. So the operator norm of both of these things are at most O of n. So you square them, you get O of n squared. So then what we see is that epsilon that we need, the n that we need is simply t squared times n squared divided by epsilon. Therefore, plugging that into here, we're going to get t squared times n cubed divided by epsilon. So this is a way in which that people estimate the gate complexity. So, okay. So I should just note that I'm not going to go into the details, but I should note that there are, of course, higher order Trotter Suzuki decompositions. So instead of doing things like e to the minus iat, e to the minus ipt, you can consider this other decomposition. And once you work out, I guess I forgot I here. Once you work out the Taylor expansion, you'll be able to see that the left-hand side and the right-hand side matches up to the second order, not just the zeros in the first order. And with this, you can get a higher order suppressions so that the scaling that you're going to get will be better than what you have here, both in terms of t and epsilon. So that's what many people are working on, like how do you make the time evolution simulation algorithm much more efficient in terms of the scaling of inverse precision epsilon, the system size n, and the time t. So Trotter Suzuki decomposition was like, the good thing is that, yeah, there is a question.
Okay, so can you go back to this previous example of this?
Mm-hmm.
Yes, here. So as far as I'm understanding, the error is coming from the approximation of the unit operator.
Yes, right. That's right.
So here, this X energy,
Mm-hmm.
there's a simple gate, right?
Mm-hmm. Yes.
I thought that the error on X would be 0 and error on Gi plus 1 would be also 0 because you have also gate, right?
So I'm assuming that those gates are perfect here.
Yes.
but the approximation, the error is coming from the fact that I'm approximating this thing by this Trotter decomposition. So that's
Yes,
where the error is.
then you have error, but for the left down part, the error on the A and B commute.
Okay, yes.
Yeah, yes. Here, because the A and B, they are simple gate, and there are no error because it's just you can write
Oh,
this.
yes, but here it's not about the gates, but it's more like so this is just the
But you take this A and the sum of the GI plus 1 and B is the sum of XI, and then it's perfect gate. You don't need any
yeah, but the
approximation.
thing is, like, for example, like, let's say I have like Z1, Z2, commutator X1, then this would be 2 Y1, Z2, if you do the arithmetics. And this has an operator norm of 2, actually. So this is not about approximation error. Here we're just trying to estimate the energy scale, so to speak. So like one way to think about this is that if you rescale A by like a factor of 100, if you rescale A and B both by a factor of 100, then that's equivalent to increasing your simulation time by 100. So like that factor has to come in, right? So it's really the norm of the Hamiltonian that you're trying to estimate here. So what it says is that if your energy scale is larger, the time scale that you're trying to simulate is larger, then you're going to need more cost. Okay. Right. So, okay. So to summarize, what's good about the Trotter-Suzuki decomposition is that it's very simple and intuitive, and it actually works very well in practice too. So even though the complexity of the Trotter-Suzuki is not the best, there are better methods. In practice, this seems to work pretty well. But the bad thing is that it is not optimal. There are better methods that are out there, which is less intuitive. Yeah, so I guess in the next lecture, I'm going to tell you about the basic idea behind what's known as the post-Trotter methods, something that doesn't use the Trotter-Suzuki decomposition. Yeah, so that's it for the first lecture. If you have any questions, I'm here to answer.
Okay, so question in the lecture room. Or question in the Zoom. Okay, I think that, okay, so one question there, yes.
Yeah, I have one quick question. So this decomposition assumes that A and B are Hermitian, right?
Yes, that okay. So I assumed it, but
Because when you prove the inequality, you use the fact that A and B are Hermitian.
yes, yeah, you're right. Because yeah, what should I say? So in this slide, I used the fact that A and B are Hermitian. Yes. So, but I guess.
Is it true that even if they are non-Hermitian, or they have to be Hermitian?
Then there will be a factor which will be well, we can go through this very quickly. There will like let's see. Okay, so up to this point, it's just an equality, so everything is okay. This part is also fine because it's the triangle inequality. But at this point, implicitly, we're assuming that from here to here, we're assuming we're using this fact, which is true. But when A and H are not Hermitian, this will not be upper bounded by 1. So like you might get something that is exponentially blowing up with the system size. Yeah, I should note that this reference talks about all of this, even when things are non-Hermitian.
So if there's no further question, then we may need coffee break, 15 minutes. So we'll meet 15 minutes later. Okay, see you. Yes, sir. Yes.